Thanks everybody for joining us again. So it's a great pleasure to have Professor Jose-Miguel Hernández-Lobato here. So Jose-Miguel has done a lot of research on generative AI, generative models for molecules. So very happy to hear from what you have to say. Thank you.
Great. Good. Thanks. It's great to be here. And I'm going to tell you about some applications of generative models in the modeling of molecules. Okay? And I'm going to start by giving some brief introduction and motivation. We are going to be working with molecules, and molecules are formed by atoms, and the atoms are not rigid. Okay? They are going to be moving in space, and they're going to be vibrating. Okay? And they're going to be adopting different configurations in 3D space according to this probability distribution, which is going to be given by an exponential of minus the energy and some constants. Okay? And this is often called the Boltzmann distribution. And an example of configurations that the atoms can take in space is given by this simulation. This is a simulation done by a company, Shore Research, that is specialized in molecular dynamics simulations. And they design supercomputers to do these simulations. Okay? This shows a big molecule, a protein, and a drug-like molecule. The drug-like molecule is floating around, and then we see that it binds to an active site there. And the atoms are not fixed. They are moving and vibrating. This is because there is nothing in between the atoms, no? So they will always be vibrating there. There is no thing that can slow them down. So we're interested in this type of simulations and modeling molecules like this because, for example, we may want to know if a drug-like molecule like this one is going to bind to a protein or not. This can be super useful to design new drugs. Okay? So we're interested in answering these questions, and we will be interested in simulating molecules like this. The way these simulations are done is typically with Markov chain Monte Carlo methods. In particular, some simulations based on Hamiltonian dynamics. You may have heard about Hamiltonian Monte Carlo. The idea is that you initialize your simulation with some initial value, and then you just apply some transition operator that is going to keep the distribution. Is going to keep the distribution, the target distribution that we want to sample from invariant, and eventually the marginal distribution of the samples is going to follow the target. The problem with this is that it's very expensive and inefficient. Okay? If you think about these Markov Monte Carlo methods, you generate the next sample in your chain, ignoring all the samples that you generated in the past. Okay? And that's quite inefficient. You could think about using generative models to do this type of simulations. Okay? Generative models are going to take some tractable noise, for example, samples from a Gaussian, or samples that you already have available. You are going to transform them through a neural network into approximate samples that are close to the target. Okay? And this can be done right away. You can generate samples that are independent. Your samples in the Markov chain Monte Carlo method, these samples are correlated. And the decorrelation time could be very long. Okay? So there is a lot of excitement at the moment in trying to use generative models to simulate molecules. Okay? And you could think that the future of molecular simulations could be highly influenced by generative AI. You may have. Okay. You have seen, for example, these generative AI methods that they can generate images, for example, from a dog based on a prompt, and the images can be quite realistic. You could think that in the future, maybe these simulations for molecules could be generated by AI instead of running these expensive simulations. You may have some prompt describing the conditions of your simulation. You have maybe a protein with some solvent given by water molecules. All these little dots are water molecules that are surrounding this protein. And you may get just your simulation right away in one shot without having to run these expensive Markov-Chain Monte Carlo methods. Right now, the technology is not really there, and it's probably that you may have in the future things that combine also Markov-Chain Monte Carlo methods and generative models. And today I'm going to tell you about some methods that work in this line. I'm going to tell you about a FEED. It's a method for estimating free energies, and this is going to allow us to know what's going to happen in the real world. Is, for example, a molecule going to dissolve in water or not? With these methods that calculate free energy differences, we will be able to do this. I'm going to give you now a more in-depth description of what I mean. This is some joint work with several collaborators and PhD students. Yaoyun, Yang Chi, Francisco Vargas, Yuanqing Wang, Carla Gomez, and Eric van den Eygen. And Yaoyun and Yuanqi are the main contributors in this work, and they deserve most of the credit for this. So I'm going to start with some problems that we might be interested in solving. We may have a drug-like molecule, like the one shown here in the figure, like this one here. And we may want to know if this molecule will be happy to be mixed in water. Okay? Maybe the molecule is happy to be surrounded by water molecules, or the molecule won't be happy, and in general, the molecule will stay away from the water. Okay? If you want to design new drugs, you want your molecules to be happy surrounded by water molecules. Okay? Because otherwise, if you take a pill, the molecule is not going to go into your bloodstream. So this is an important problem in drug design, and you want to design molecules that have high solubility. And we want to know what's going to happen in the real world. Is the molecule going to be mixed with the water or not? It turns out we don't really need to do a real-world experiment to know this. You can do simulations of molecules, and you can get an answer to this question. Okay? One thing that I didn't mention is when I talk about this Boltzmann distribution, there is an energy here. This energy comes from a model based on physics. Okay? And I didn't mention where it comes from. There are many different options for this. Many times, this energy could be given by a machine learning model that has been trained on data collected by running simulations also based on quantum mechanics. Okay? I'm not going to go into the details of this, but you can get very accurate models for this. Yes, one question?
What is it, the energy of? Sorry.
Why?
The energy of?
What it means to get some energy.
Yeah.
Okay. Think about, for example, two atoms. For example, like a hydrogen-oxygen atoms. These atoms, they would like to be close to each other. And you could think about trying to put the atoms together. If you try to put the atoms together, they are going to be attracting a little bit. And then once they are too close, they won't want to be more close. Okay? So if you want to put them too close, you will need to increase the energy. Okay? You could think about some function that tells you how hard it would be to put them together, and this would be like the energy of the configuration. And if you think of...
It's the energy it would take to keep them in that specific...
Sorry?
So it's the energy it would take to keep them in that specific...
Yeah, in that specific configuration. Okay? And then what is going to happen is that some configurations have lower energy. And then the atoms are going to be happy in those configurations. And configurations that have very high energy are less likely to happen. And that's why you have minus the energy here. Good. Any other question? No? Great. So we want to know what's going to happen in the real world. And we have these two states. One state, the molecule is surrounded by water molecules. Another state, the molecule is separated from those. And you could imagine this space, X, that represents configurations of 3D positions of atoms. This area could represent configurations where the molecule is surrounded by water molecules in state A, and this space here of 3D configurations is where the molecule is separated from the water molecules, okay? And they are going to have different energies and different probability mass for those states, okay? So the energy, from the energy you go to probabilities by taking exponential of minus the energy. I'm writing now U to denote the energy here, and this thing here is the log normalization constant of the distribution, okay? So what's going to happen in the real world? Is going to be the molecule surrounded by water or not? It depends on the probability mass of these modes, okay? If I know the probability mass of these modes, how much probability mass is under the curve here and under this curve, what is going to happen is what is more likely to happen in the real world, okay? And this difference between the normalization constants of these distributions, this thing here is called the free energy difference. And this is what you are very often interested in calculating, okay? And the question is, how do you get this free energy difference? We are going to see today what is the state-of-the-art method to solve this type of problems, and we're going to propose some new contributions in this area. Is there any question on this? Yes?
What's the dimension of X usually?
X is going to be the 3D spatial coordinates of all the atoms in your molecules of interest. So in the case of the drug-like molecule surrounded by water molecules, your molecule could have 10 atoms, maybe, I don't know. It depends, or it could be bigger. It could be even a protein, so it could be thousands of atoms. It could be quite large. But think about the atoms that are in your molecule, 3 times the number of atoms. Those are coordinates. And now you have water molecules. If you want to have an accurate simulation, maybe you have hundreds of water molecules, a large number of water molecules. And for each water molecule, you have 3 atoms and 3 spatial coordinates, so the dimensionality can be quite high in practice. Yeah.
And the energy function, it's always physics-based, like it's always known for...
Yeah, I mean, the easiest thing would be, I mean, it depends on the models that you use for the energy. Some very simple models, you typically call these force fields. Some very simple models could be like thinking about springs. You have like hypothetical springs attached to the atoms, and obviously the atoms will be able to move, but they cannot get very far from each other or not too close to each other. And those could be very simple models. They are not so accurate. Most accurate models now, they use graph neural networks. You could have a graph neural network model that is going to predict accurate energies, for example. Good. So we're interested in this. And how do we get this free energy difference? One way to do it is to obtain interpolating distributions between the probability distributions for state A. Here you have a probability distribution for state A. Here another probability distribution for state B. And what you can do is create interpolating distributions between the two. There are different ways in which you could do this. A very simple way to do it is just to do a linear combination of the energies, okay? And you take exponential of minus this linear combination of the energies of the two, and you can interpolate from one distribution and the other. That could be one way. There are many other things that you could do. But let's assume that you get these interpolating distributions, and now you generate samples from the distributions, okay? So for each distribution M, you're going to generate, for example, n samples, okay? So you have a total capital M distributions, and then on each distribution you generate capital N samples. You can then try to estimate the normalization constants of the distributions. That's basically the problem that you want to solve. Estimate the normalization constants of these distributions. How can you do that? Imagine that there are only 2 distributions, PA and P2, What I can have is then samples from these distributions obtained by Markov chain Monte Carlo. That's how people do this now. So you may have samples here from the first distribution PA, okay? And now I may have also samples here from the second distribution P2. And my problem is to estimate the normalization constants of this distribution is basically the height of these density curves. What should be the right height? I can scale them by multiplying them by a constant. The way to estimate the right height, one way to estimate this right height for the distributions is to solve a classification problem. A classification problem using a generative classifier, okay? The probability that a sample, imagine that I have 1,000 samples from each distribution, the probability that one sample comes from distribution A is going to be PAX divided by PAX plus P2X, okay? And I can calculate these probabilities, and obviously I can scale, this could be a normalized distributions, and I have constants determining their scale. I may want to use these probabilities to solve the classification problem. That's what you do typically with a generative classifier. You may have heard about naive Bayes. Have you heard about naive Bayes as a generative classifier? Okay, this is exactly the same. Now, in the prior probability for the data for each class is the same. You have the same number of samples from each distribution. And the only thing is the densities up to a constant that change. And that's what your generative classifier is going to do. And you can get the probability of one class or the other using Bayes' rule, which is given by this ratio. You can find the normalization constants by solving the classification problem by maximum likelihood. Okay? You have your generative classifier, you can maximize the likelihood, and you will estimate the normalization constants. This is the best existing method for solving this problem. And you can show that it has a minimum variance in the estimation of the normalization constants, which is great. Okay? This method is called M-bar, and I have this slide here. It basically says what I mentioned before. You have now data from all the different distributions, not only two. You have data from all these different distributions, and you solve now a multi-class classification problem, where you use a generative classifier using these distributions. Okay? So you have that the prior probability for the class labels is now the same for all classes. Yes, one question.
On the distributions on the previous slide, for the intermediate ones, the blue ones, are we generating samples?
Yes, we are having samples from all of them. So we have n samples from each distribution.
So the sort of first and last distributions are the models that
they are the ones we care about. We care about the first and the last one, but we're going to use the intermediate ones to help calculate the normalization constants.
And then where do the samples in the intermediate ones come from? Are those like other?
What is the question?
So the samples in the red distributions are from
the red distribution. So you have samples from each distribution, but you are going to assume that you don't know from which distribution the samples come from.
Okay.
And you have ground truth labels that tell you, oh, this sample comes from this distribution, but I assume that I don't know the distribution. I try to guess from which distribution the sample comes from by using these conditional probabilities. Okay? It's going to be maybe more clear when I show the equations. So the prior probability of each sample belonging to a particular distribution is 1 over the number of distributions. It's uniform. And now the conditional probability of given the sample here, I have a sample now, and I want to know, oh, is this belonging to the kth distribution? That's going to be proportional to the prior, which is a constant. You can ignore that. And then here you have the probability that the kth distribution gives to that sample. The kth distribution is going to be exponential of minus the energy of that distribution minus the log normalizer. And this is what I don't know. This is going to be a parameter. And it's determining the height of my distribution. Okay? Then this is the conditional probability using Bayes' rule is the same as what I mentioned before. It's just the probability that the distribution, the K distribution gives to the sample divided by the sum of the probabilities that the other distributions give to the samples. These are normalized distributions, but the whole thing works equally. And I can evaluate the log likelihood over my data, log over the product of data points, and then each sample could come from any of the distributions. And yeah, you can maximize the likelihood, calculating the gradient. I'm going to go a bit faster on this because it's just some derivations, but you can calculate the gradient of the log likelihood, and you will get an expression like this that tells you the value of the log normalizer of the mth distribution in terms of the values of the log normalizers of the other distributions. There is no closed form solution. It's like in logistic regression. You don't have an analytic solution for the maximum likelihood value of your weights in a logistic classifier, but you can do iterative optimization to find the maximum likelihood estimate. Here we need to do iterative optimization as well. Okay, so you have now these equations, and given some initial value of the log normalizers, maybe you initialize them to 0. You then update the values of the log normalizers as a function of the values of other log normalizers. Okay, you just iterate this, and at convergence you get point estimates for the log normalizers, and that's it. Okay, you are done. This method is the most efficient one for solving this problem. Why it works, or when it's going to work? It's going to work when you have overlap between these distributions. You need to be able to find the right normalization constant between PA and P2. You need overlap between the samples so that you can accurately estimate this, or accurately solve the classification problem. If there is no overlap between the samples, you cannot estimate the right height of the distributions. Okay? You need to see, you need to have overlapping samples. You're going to have some fraction of samples that appear in some region from one distribution and from the other, and the right height of the curves will come from that fraction of samples. So if you don't have overlapping between these distributions, you won't be able to solve this problem very well. And that's why you create these intermediate distributions with high overlap. Okay? Yes?
So each of these samples is one sort of configuration
of the molecules. Yes, that's right.
So do the intermediate distributions sort of represent like it being a bit soluble in it?
No. So I can tell you what the intermediate distributions could be in practice. Imagine you have this energy model. This energy model can have some terms that come from the interactions between the water molecules and the drug-like molecule. And what you can do is switch off those interactions. You have some parameters that determine the strength of those interactions, and here you have full interaction. Here there is no interaction, and it's like having just water in vacuum and the molecule in vacuum completely separate. So that's how the distributions could be changing. Yes?
How do you know if the method works when you train a classifier and maybe you're overfitted, you're underfitted? How do you know that it works?
That's a very good question. There are methods to get some confidence bands in this. I'm not going to mention that, but there are some methods that will tell you some confidence in your estimate of the normalization constant.
And is the method described in the paper that was in the footnotes?
Yes. So this is called, where is it? Yeah, it's this paper, MBAR. Okay. MBAR comes from BAR, which is Bennett's acceptance ratio, and MBAR is from the fact that you have multiple distributions. BAR only works with 2 distributions, MBAR works with many interpolating distributions.
How many samples do you usually need to get good error
I think it depends on the problem. I can give you an example that sometimes you use 500 samples. But
How many dimensions?
it could be very high.
And it works?
If you have high overlap, then it's going to work. Good. So this method is great, but you need to require samples from the intermediate distributions. Okay? Imagine that maybe generating these samples is very expensive, and maybe you only have samples from the first and the last distribution, or just assume that you don't have them. I mean, this is what the setting that we work on here. We are going to assume now that there are no samples from intermediate distributions. I only have these two distributions. You could try to apply the same method that we have seen before, embark only in the two distribution setting, and it's not going to work because there is no overlap between the distributions. Okay? We are going to see now methods that you can use to solve this problem, and that are based also on generative models. Okay? Yes?
You only need the samples, or you also need the energy of each of the samples?
You will need the energies of the distributions. Yes, that's right. Yes, and to solve M-bar, you will need the samples. So yes, maybe that's to clarify. So here you need, for each of sample, it doesn't matter what distribution it was sampled from, you need to evaluate the energy of all the distributions on that sample. Good. So some notation, we are going to denote these anormalized distributions with a tilde here. It's just the exponential of minus the energy with no constant. The normalization constant is going to be Z. The free energy is going to be minus the log normalizer. And the free energy difference is going to be just the difference between these two values. Okay? Good. So what do you do when you don't have intermediate distributions? You can do, you could try to solve the problem ignoring the fact that you don't have intermediate distributions and just work with two samples, with two distributions. You can do importance sampling. Okay, many of you have seen importance sampling before. Who has seen importance sampling? Okay, some people have seen it. The idea is very simple. The log normalizer, the free energy difference is the difference between log normalizers, is this ratio. Z2 here is just this integral of the normalized distribution. And now you can multiply and divide by p tilde. And then this Z1 with a p tilde, you can put it together, and you will have the normalized version of P1. And then here you just have the ratio between anormalized densities. And this integral of P1 times this exponential of the difference between energies is just minus the log of the expectation with respect to the first distribution of exponential of the difference between energies. This is importance sampling. It's a method to estimate integrals when you can sample from a distribution and you just average over samples of that distribution. So here we have some samples from the first distribution, and then we average this, and we would get the difference in normalization constants. The problem is that this has high variance, okay? And people don't use this in practice because of that. This difference between the exponential of minus the energies, the exponential of the energy difference is going to have high variance unless there is a lot of overlap between the distributions, which is probably not going to happen in practice. You could do this, but it's inefficient and it has high variance. You can do something similar to this M-bar, but only with two distributions, and it's called bar, and it's this Bennett's acceptance ratio. It's what was proposed before M-bar. People proposed it only for two distributions, but then they came with interpolating thing. And this is a recursive algorithm, an iterative algorithm to estimate the free energy difference. It's similar to M-bar. You start with a guess for the free energy difference, this C, and then you have this function G, which is the Fermi's function, and you just iterate. It's almost the same as the M-bar. It's slightly different, the formulation, but the fixed point is the same. And you can estimate the free energy difference using this method, but if there is no overlap between these distributions, you're going to still suffer. It has less variance than the importance sampling. This has the smallest asymptotic variance, this estimator, but it's going to still suffer if there is no overlap between the distributions. You can do something to improve things and to improve the overlap, and you can use a transformation of your samples from the first distribution. You can transform them using a bijection, and you can get now samples from another distribution P1 that has more overlap with the target, okay? And you could just do importance sampling, and now you have high overlap, things will be better. Typically, the way you do this transformation, or what people have proposed, is to use flow matching. You can use a continuous normalizing flow that is going to transform your data. So you are going to have a transformation, an evolution of x. You maybe have that x0 is sampled from P1, and you have that then you are going to evolve the samples according to a vector field. This will depend on t as well. Okay, we have that we start with samples from the first distribution, and then we have a vector field ut that is going to tell us how to update these samples according to this differential equation. And you can show that the log probability at time t of xt is going to be the log probability at time 0 of x, and then here you are going to have some integral, and there is like a divergence here operator of us xs d. Sorry, this should be t. Okay, this is t. Yeah. ds. Okay. This is a flow matching, continuous normalizing flows. It's a way of transforming your samples in an invertible way, and you could think of learning this transformation from data to increase the overlap. Okay, that's what people have proposed in some of these papers. The problem is that you need to calculate this density of the transformed samples, and you need to solve this integral here. This is a t, just to make it clear. This is a divergence operator. This is the sum of the gradient of this vector field with respect to, for each output, for each dimension of the function of for each dimension in the output of the function, you need to calculate the gradient, and then you need to sum all of them. And this is usually expensive, okay? So that's not great, and what we propose here is a different way. We're going to transform the samples in a way that we have high overlap, but we're going to do it not with these continuous normalizing flows. We're going to use stochastic differential equations, okay? And we're going to have one stochastic differential equation. We're going to have here that x0 is a sample from the first distribution, and x1 is a sample from the second distribution, okay? And we're going to have now stochastic differential equations mapping sample from x0 into other transformed samples that ideally are samples from the target PB at time 1, okay? So we have one SDE that goes from time 0 to time 1 and maps samples from PA to PB into samples from PB, and then we have samples from T1 that are from the PB distribution, and they are mapped into samples at time 0 from the PA distribution, okay? This is an SDE that runs forward in time, and it maps x0 to x1, and this is an SDE that runs backward in time, and it maps x1 into x0, okay? There is a very good reason why we may want to use these SDEs, and the main reason is that we won't have to use these formula with this integral of this divergence operator to calculate the change in the probability density. Okay, we will be able to calculate the free energy difference without having to do this expensive integral. Is it clear why you need to solve this integral? It's because if you need to do important sampling between P1 prime and P2, you need the density of P1 prime. Okay, and to get that density, you need to solve this.
What does it mean for it to go forward in time and backwards in?
Yeah, it's how you solve the SDE. We're going to see an example in practice. Typically, you solve these SDEs with a discretization, and you will discretize your time. And when you solve it backwards, you start with a sample from PB, and then you will evaluate some of these drift terms on the samples. You evaluate the drift term on the sample at high time when you go backwards in time, and at low time when you go forward in time. We're going to see the equations, and you will see the difference.
As the time dimension changes, is the location of the atoms?
Forget about the atoms here. We are going to see, you will have to numerically approximate the solution to these SDs, and you can do it discretizing the time variable. And the changes will be on where you evaluate these functions that appear here. Okay? Just to clarify, these SDs, you have some drift terms here that are deterministic. You have some current value, xt, you can evaluate these functions, and then you add Gaussian noise. This represents Brownian motion, and it's like a small, infinitesimally small Gaussian noise that is added, and it has some scale. But this thing is deterministic. And you have here now these two terms, u, and small u, and big U. Okay? And I'm going to tell you what these things are. So big U is the energy of the marginal distribution of the samples generated by the SDs. Okay? The SDs, they just generate new samples at any time xt. They are going to generate some samples, and you are going to have a marginal distribution for those samples. Okay? So you could imagine that this thing, the probability of xt is going to be proportional to exponential of minus big U t xt. Okay? And then this other thing here, lowercase u, is a control thing that is going to ensure that the marginal distribution has this energy. There is a bit of a recurrence here in the definition, but we're going to see how you obtain these things in practice later. Okay? The ideal thing is that you have kind of some marginal distributions, and then the SDs will generate data from following those marginals by using these specific terms. And the distribution that you get in the forward and in the backward direction are the same. Okay? These SDs are going to be a flexible mapping between the distributions. And the most interesting thing is that they allow us now to calculate this free energy difference without doing this integral, which is expensive. We don't have to do this. Okay? I'm going to tell you now how that works. Any questions so far? No? So this is an example of how the SDs would be mapping distributions. So you have here now some distribution. The SDs are going to be moving in time. This is time 0 here. This is time 1. And then at time 1, you have a different distribution. Okay? And you could imagine these SDs as you follow some trend. There is like a deterministic trend, but there is some small amount of Gaussian noise added there. So how do you solve the SDs, and how do you get the normalization constant difference? You solve the SDs by discretizing the time. So you have this unit interval from time 0 to time 1, and you're going to discretize it in m values. You take m points in between 0 and 1, capital M in between 0 and 1, including 0 and 1. And now you are going to have a discretized forward SDE, which starts with a sample from PA. And now you have this sample here. You feed it into a capital U and a small u, and you add some small amount of Gaussian noise here, and you get the next value. Okay? So you start at x0, you will get x. You start at x0 or at x of t1, and you get x of t1 in this way. And the backward SDE starts with a sample from x1, from PB, a sample x1, and you solve it backwards by evaluating now the, you have here the function at time 1, and then now you evaluate at that function at time 1 to get the trend, okay? So if you think about where you are evaluating, the functions here in the drift, for the SDE, you evaluate them at different points, okay? If you think about each time you make a step, you will be evaluating them at different points. Yes?
Maybe I'm wrong, but the sign of the second term, the second equation, should that be the opposite of the sign of the second term of the first equation?
You mean for the...
This same slide.
Yeah, there could be a typo here. Yes, I think, yeah, there is a typo. Yeah. This should be minus plus.
Because the third term has opposite signs, but the second term doesn't have opposite
Yeah.
signs.
Yeah, I think there are some typos here. I think this should be plus here and here.
Third term has opposite sign to the first equation already, but first line plus second line.
Yeah, I think this should be like this. Good. So, yeah, so you can then solve these models forward and backwards, and you will get some samples. And it turns out that you can calculate the difference in normalization constants now using importance sampling here. So this will be, this is an expectation here over x in the forward direction, and this is in the backward direction here. And here we are averaging over samples from the forward SDE. We are dividing by the probability of the generated samples. The probability of generated samples is the probability of given by PA of x0, and then the Gaussian densities for these transformations given by the SDE. Yes?
So you mentioned before that your laptop is about
Sorry.
You mentioned before that importance sampling will have a high variance. It's not very good at estimating this. So how is this case different?
Yeah, let me... Sometimes my laptop doesn't is this connected? Well, not. No. But this should work if I just place it well. Let me see. Okay, now it's charging. Yeah, sorry, what was your question?
Yeah, you mentioned before that importance sampling here has a high variance.
Yes, we are going to deal with that. We are going to deal with that later. So yes, you have to be careful because importance sampling can have high variance. The good news is if you have these SDs with a large number of steps and with the right terms here, this variance can be super small. It could be arbitrarily small, assuming that you learn, in practice what we are going to do is learn these terms, U and capital U and lowercase u, we are going to learn them from data. If you learn them perfectly, you could have like zero variance. Obviously, that's not going to be the case in practice, but you could in principle reduce variance by doing this. And you will have less variance than not doing any transformation.
And even for very high dimensions, you would still have
it will be better than not doing this. I mean, not doing this would be just forget about these Gaussian terms here. And it will be better to do this. Yes, but it could be still high variance in high dimensions. Good. So you can do this density, you can calculate these importance sampling estimators, and you can do it by doing importance sampling from A to B or from B to A, but you can still have high variance. And what can you do to, I'm going to maybe skip this slide in the interest of time. What can you do to reduce variance? You can do the same thing that we did before with M-bar. But now we are working with these trajectories of the SDEs instead of with the samples themselves. Okay? So now you can try to solve this classification problem where what you have is not original samples from A and B, but what you have are trajectories from the SDEs in the forward and in the backward direction. And you want to try to classify a trajectory if it came from the forward SDE model or from the backward SDE model. Okay? And the good thing is that now you're going to have quite a lot of overlap between these trajectories because you have learned these SDEs to closely match each other. Okay? So you can do some bar-style minimum variance method, and it's the same thing as before, but now you are going to be working with these densities ratios in the forward and the backward discretized SDE. Okay? And that's it. And this will reduce variance massively. We're going to see examples later. How do you get the SDEs? I didn't say anything about this. Okay? It turns out that there is actually a method to learn these SDEs, and it's called the stochastic interpolance framework. Who has heard about the stochastic interpolance? Some people have. It's a combination of, it's something in between flow matching and diffusion, okay? I'm not going to give you a lot of details on this here because you can go and look at the paper and see how it works. But the key thing is that what you're going to do is to generate data from the SDEs, and you can actually do that using this interpolance, okay? The interpolant is going to be now a data point, xt, that you obtain it by doing a linear combination between samples from A and B in a way that at time 0 you get the sample from, so if you imagine that you have a sample XA from A, a sample XB from B, and now you do a linear combination of them or some type of interpolation between them in a way that at time 0 you get XA and at time 1 you get XB. And there's like a continuous function interpolating between the two. It could be nonlinear, this function. And then you add a little bit of Gaussian noise here. Okay? This generates now samples whose marginals are distributions that interpolate between PA and PB. Okay? And the good news is that given these samples, you can generate these samples because you have samples from A and samples from B, and you can add the Gaussian noise. So you can sample from this. It turns out that then you can learn the terms in your SDEs using the fact that they are equal to some conditional expectations. So lowercase u is going to be this conditional expectation of the derivative of the interpolant. I can compute the derivative of this with respect to t. And ut evaluated at x is this conditional expectation. The gradient of the energy is given by this conditional expectation. And you can learn now these functions by minimizing squared errors. The minimizer of a squared error is a conditional expectation, and you can just optimize these losses with neural network models here that are going to depend on some parameters. You have one model for lowercase u, another model for the gradient of capital U, and that's it. This, you learn it in this is basically a score matching, denoising score matching. You have seen this in the previous talk about diffusion. No, I assume you have seen this. This is slightly different, but this is what you do in flow matching. And yeah, in the end, it's more or less the same thing. You just minimize now a squared loss, but you have the gradient of the interpolant. Okay? Yes?
What's the interpretation of lowercase u here?
It's a control variable that is going to guarantee that the SD samples have this a marginal with this energy. So it's I mean, let's think what happens. So if we go to the SDEs, you could forget about the U, okay? And this is going to look very similar to Langevin dynamics, okay? You're running Langevin dynamics trying to sample from this distribution, but the problem is that this distribution is changing as a function of time. So Langevin dynamics will be tracking U and trying to sample from that, but the U is changing and you never really sample from U, okay? And if you really want your Langevin dynamics samples to sample from the distribution whose energy is U, you need to add a correction term, and it's this correction term.
So that's related to like the log determinant of the gradient or derivative or something?
The control variable? No, I don't think so. Yes, more questions?
Are the, other than the Gaussian noise, other forward and backward SDs symmetric?
Can you repeat that?
Are they symmetric? So if I've gone from a point in A to a point in B, and then I go backwards from the point in B, will I get the same point back in A, other than the Gaussian noise?
If you use the same, I think quite likely if you use the same noise, given the same noise, yes, and using an infinite number of steps, my impression is that that will be the case. Yeah, I think that would be the case. But you will need perfectly learned functions here, and that's not going to be the case. These formulas that I have here, they still work if you have imperfect functions, okay? Because this is important sampling. Important sampling is unbiased, even if you don't have, if these forward and backward models are not the same, it will still work. And the same for this bar style method. Good. Any questions? Any more questions on this? No? Yes. This here? Yes, this delta here, you would replace this expectation by an empirical average. So you will have samples from A, maybe 1,000 samples. You then use your forward SDE to generate trajectories forward, 1,000 forward trajectories. And then you just calculate this density ratio between the forward and the backward model on those trajectories, and you average. Good. So how does this work in practice? We tested it on different problems. The first one is a Gaussian mixture model. The first state, this is with Gaussian mixture models. The first state, PA, is a Gaussian mixture distribution where you have 16 modes. And the second one is a 14-mode Gaussian mixture distribution. And you're going to be now interpolating between these two distributions. The second problem is a problem where you have particles, and these particles are going to be interacting with each other according to a particular force field given by this Leonard-Jones potential, or you just switch off that and they don't interact. Okay. Then another one is with a molecule, an alanine dipeptide. This is a small amino acid. It's an amino acid, and we have that in one state is just in vacuum, And in the second state, there is like a change in the energy given by some implicit solvent. So we assume that there is some solvent, like water molecules around the amino acid, and that's going to change the energies. This is implicit, so there are no real water molecules there, but the energy changes. And then the other one is this alanine dipeptide, where this alanine dipeptide, it's like a flexible molecule, and the angle between some of the bonds in the molecule can change, and in particular, this angle phi can change, and we're going to consider one state where the angle takes these values. This would be, for example, a state A, and then another state where the angle takes other values, okay? And we want to calculate the free energy difference in that case. It's like thinking that you have a multivariate distribution, maybe like this, and then you take one mode here. This is the probability of state A, and this would be for another mode, the probability of state B, okay? We calculated with a reference, which is M bar, where you have data from the intermediate distributions. And this would be kind of the ground truth value. Obviously, in the mixture of Gaussian model, you know that the distributions are normalized, and the difference should be 0, because both have the same integral, which is 1. We compare with a target FEP, which uses flow matching, and it's going to be expensive because you need to solve this integral to calculate the density of the transformed samples. And that's why in these Leonard-Jones problems, where we use this number of particles, 79, which is quite high, for this, for that method doesn't work. You cannot really run that method, it's too expensive, okay? But you can still run our method because it doesn't involve calculating these expensive integrals. We compare with neural thermodynamic integration, which is another method. This is based on diffusion. You learn a diffusion model, and you use that to approximate the free energy difference. And in general, we get better results closer to the reference values in most problems. We can see here the gains of this minimum variance estimator, okay? You can do just importance sampling on these forward-backward trajectories of the SDEs, or you could use the minimum variance estimator, and you can see in this Leonard-Jones problem, this would be the number of mini batches that you process during training to train these functions U, big U, and small u. And the minimum variance estimator converges very quickly to the right solution, while the other one, it converges very slowly. And this is for the alanine dipeptide problem, and we can see that we converge much faster by using this improved estimator. Good. So just to conclude, I have described here this method FEED, free energy estimators with adaptive transport using these stochastic differential equations to transport the samples. It calculates free energy differences using only samples from the initial and final state. It doesn't use intermediate distributions. It doesn't need samples from the intermediate distributions. Because of that, it works by using these SDEs that flexibly map between one distribution and the other. It avoids calculating expensive changes in the density, which is what flow matching needs to do. We use a bar-style minimum variance estimator, which helps quite a lot. And we have seen that it outperforms other baselines, like this neural target FEP and neural thermodynamic integration. There are limitations in this method, obviously. The first thing is that you need to learn the coefficients, U, lower u, and small and big, small u and big U. You need to learn that from data, and that will take time. The good thing is that maybe these neural networks could generalize. And if you have to solve a collection of problems, you can reuse whatever you learned. Imagine that you want to calculate the solvation free energy difference for drug-like molecules. Maybe you learn these SDEs on a collection of molecules, and then you get a new drug-like molecule, and you could just reuse the SDEs. Obviously, your SDEs models will have to generalize in that case. Good. Thanks, everyone.